Okay, hello everybody. Thanks for coming. Today it's my great pleasure to present you the work of Professor Gregor Trimmel. I would like to say a little bit of his research history. So Gregor finished studies Master in Technical Chemistry in the Technical University in Vienna in 1996. And then he continued with PhD study at the same university. At that time he was studying the organic and inorganic hybrid materials using these organically modified alcohol oxides for the synthesis of nanostructured materials. And then Gregor went to a postdoc into Paris, into the University of Pierre and Marie Curie, and then immediately after to Padova. And he came back to, then he came to the Graz, if I'm right, yes. So he started his research at the Technical University in Graz in 2002, so just 2 years after his PhD study. So there he was spent 6 years, and then he received habilitation for macromolecular chemistry and technology. And then he was working with functional polymers and patterned surface layers. In the period between 2008 and 2013, Gregor was a director of the Christian Doppler laboratory for nanocomposite solar cells. And just before COVID in 2019, he was appointed as a full professor. And since then, he's leading the photovoltaic research group at the Technical University in Graz. So to sum up, Professor Trimmel is actively working in the field of organic solar cells, in the research of new materials for these organic solar cells, and also perovskite solar cells, and this is doing since 2004. So I think we are all looking forward to this opportunity that we see that he will share us with his experience in the presentation of organic solar cells. So Gregor, the stage is yours.
Thank you. Okay, thank you. Egon, very nice introduction. I almost forget how many stations I had. Welcome to this scientific afternoon. It's a very great pleasure to be here. It's very difficult to me because I don't know your scientific background or your background in general, so I try to show you some general statements on photovoltaics and organic solar cells, but I also want to show you what we are doing in our research. So I hope that it's not boring and not too far away, and that everyone can take something home. First of all, just start with a motivation. First of all, what is solar cells is photovoltaics. So what is photovoltaics? It's of course the direct conversion of light into electricity by a semiconductor, and we are talking about organic semiconductor. But before starting with organic solar cells and what we are doing, for me, always what is acting as a motivation slide is actually the situation which we have in our energy situation at the world. Because some people believe that we just put somewhere solar cells here and a wind power plant somewhere there, it is sufficient. But if you really look at our energy supply today, I think the numbers are just till 2019, but nothing has changed too much. Yeah? We see that our energy is still mainly based on fossil fuels, so it's coal, oil, gas, also biofuels, also all of this produces carbon dioxide. Of course, this is not only electricity, this is everything, transportation, heat, industrial use of energy. So if we really want to decarbonize our industry and our life, yeah, we have to do much more than to just put some solar cells somewhere else. And this is also a challenge, but this is also motivation to make better materials, to invest also research in this direction. Yeah, of course, coming back to the solar cells, of course, you know, solar cells are now everywhere. You see it in the landscape on the field, you see it probably on houses. But this is not only, I think these are the classical ways. You probably have also a lot of installation here in Slovenia, yeah. But it's not only this applications you see. For example, floating PV is an emerging field. You see, of course, building integration, where you have the whole building or integrated in the shadowing, for example, of buildings. But also very nicely, you have photovoltaics which you don't see anymore. So this actually have photovoltaic tiles, or here roof tiles, which are really, so you don't have any problems with, I don't know, if you have heritage buildings like also this building, you can put red, I don't know if the roof here has a red roof or not, but you can also get it in black or in gray shadowing. Yeah? And this is also very interesting, it's a very new trend. This is agri-PV, where you have the double use of agriculture and photovoltaics. I don't know how it's the situation in Slovenia, but I think probably the same like in Austria. So the farmers are struggling because the prices for food is very low, what they get actually for the products. And here it's a very good situation that they can get money from photovoltaic electricity, but also can agriculture without any, let's say, disturbance or large disturbance. Yeah. As I mentioned, photovoltaics is evolving, so these are the annual installation for each year. They are climbing up. I think 2023 we have even above 300, 350. So it's really going fast. However, if you just look the electricity generation by source, yeah, you see it already, but nevertheless also electricity is mainly produced by coal, natural gas, a little bit by oil, yeah. But nevertheless, I started 2004, yeah, with photovoltaic research here. You even see it. The question is, of course, how much electricity do you think is created today already by solar power? The numbers are varying, so depending which publication you read, yeah. I found this number here for 2022 that already 5% of the world electricity is produced by the sun, which I think is really nice. Actually, when I started 2004, many people didn't believe that solar power can perhaps contribute to 1%, yeah, and not more. Now we have already 5%, and I found already for 2022 the number of 6%. It's perhaps a little bit overestimated, but we are now approaching really 5 to 6%. And as I mentioned last year, we have a record installation, so probably already a little bit more than the 6%. However, it's not that all countries have 6%. It's just quite unevenly distributed. Just I like statistics. Yeah. Of course, sunny countries like Spain and Malta, they are approaching now 20% of the electricity is generated by sun. Also, for example, here Greece or Australia, but also the Netherlands are approaching 50%, which is not the sunniest country who has been in the Netherlands, and also Germany, of course. It's now between 12 and 50%. Not all sunny countries are that far. So Italy, for example, has roughly 10%. And you may ask, where is Austria and Slovenia? So of course, we are also in this list. So we are roughly around 5, and also Slovenia are roughly around 5. These are, I think, so you find different numbers. I found also numbers for the same year in Austria to be a little bit lower, so below 5%. But this is the range where we are. And we have also in Austria there at the moment a very large discussion how much solar power can come into the grid, in the electricity grid. So there are some, but you see Spain has no problem with 20%. So I think we are far to having some severe problems. Photovoltaics, of course, today you see mainly silicon, but already this image from a test facility in Morocco shows you that photovoltaics is very diverse. You have different technologies. And if you just have a closer look on the technologies, They can be grouped in different regions, different technologies. So of course the major technology is silicon solar cells. So these are the blue technologies, these are the record efficiency in the lab for single solar cells. So these are, the update is always from the NREL in America. So they can reach 26%. This is major technology which you find on the rooftops. However, you can also buy some thin film technology like SiC or cadmium telluride. They are not so often found, but roughly 4 to 5% of solar panels are based on these technologies. The green one, which are also approaching silicon, they are a little bit lower, but they are also 23% the best technologies. Then of course there are special solar cells actually, which are gallium arsenide for high efficiency solar cell, for special applications, and also for very special applications, multi-junction technology, which under concentration of light can reach up to 47% efficiency. So almost half of the sunlight can be converted in electricity. So I think this is a very good idea. Yeah, good number actually already, yeah. But of course it needs mirrors or lenses to focus the light on the solar cell, and the solar cell is very complicated. Actually, you have here 4 to 5 different materials stacked on top of each other to make a very special solar cell, but this solar cell can reach already 50%. And then these are a group of material which is in red, which are the so-called emerging technologies, which actually one of them is the organic solar cell. I have a zoom in these emerging technologies actually. This actually, the organic solar cells, when I started we were roughly 3% and everyone was laughing, yeah, why do you invest money and time in this technology, which is really, if you compare to silicon, which had at this time 20%, was nothing. Yeah. But as you see, they have really gained a lot of, especially in the last 6-7 years, they had a boost in efficiency with new materials, and they have reached now 90%. And I'm working since 20 years in these emerging photovoltaic technologies, so mainly on organic solar cells, but also, sometimes on perovskite solar cells, which are even a very interesting technology, reaching now 26%. But I will not talk about this today. You might ask, of course, why organic photovoltaics? What is the special things of organic photovoltaics? Actually, it's organic material. It can be really processed with like a plastic material actually. Yeah? So you can do roll-to-roll processes. So you can actually, in the ideal case, you can start with a plastic foil, like a PET foil. You can have different coating steps, probably a little bit more complicated than shown here, yeah. But in principle, they are in one large machine actually, yeah, you can process the whole solar cell at once. So it's totally different, like the silicon technology, where you have a very complicated doping, wafer processing, then also solar cell processing, module assembling, and so on. So you can process the solar cell and the module at once, and of course you can then also close it with a transparent packaging material, and you get it really flexible, because actually the flexibility is just given by the substrate material. So if the PET foil is flexible, you have a flexible solar cell. It can be transparent or semi-transparent, yeah? And it can be patterned. So this is very easy. So it's especially for decorative, architectural applications, for building integration. It's a very attractive material. Of course, also because it's flexible, it's very ideal for outdoor uses like camping. So if you have a tent or shading elements which you can fold up, and then you can produce electricity. And it's lightweight because you don't have any glass there. Yeah, so this actually would be an ideal solution for, let's say, also transportation, for outdoor activities, for wearable electronics also, where we have some solar cells integrated. So this is, I think, the pros actually. So they're flexible, they are roll-to-roll processable. They can be semi-transparent. They weight, so you can have solar cells with below 1 kilogram per square meter. So it's really, if you have already seen a silicon solar cell module, it's quite heavy. Yeah? So this, of course, would be very quite alternative. Sorry. The cons, of course, I don't want to to neglect the cons. Yeah. So just So the stability is the problem and the costs. But we will the costs are coming because organic solar cells, they don't, also organic materials in general, they don't like oxygen and light together. So for solar cell, you cannot exclude light because then you don't have they don't not work. Yeah. So you have to exclude oxygen. And the packaging material, which really is blocking every oxygen and it's transparent, this is the most difficult task, and they are quite expensive. There are some materials, yeah, but this makes organic solar cells today still expensive. This is just some images of really flexible solar cell, some roll-to-roll processing, or for example, there are also some reports for making integrated solar cell in a sunglass, for example, yeah, where you just have really, this is only one cell actually, but this still can produce a little bit of electricity, which you can then use for a sensor or whatever. Yeah. So there are quite interesting applications here possible, which you cannot do with silicon. What are organic solar cells? So organic solar cell uses organic semiconductors. So usually you have materials which are also found in many organic dyes, which you use for, like indigo, for example, for dyeing your jeans. Or the carotene, for example, if you have the double bonds in your in vitamin D, actually, yeah. So they are materials which have double bonds or aromatic ring systems. So you have a large conjugated system which allows you to absorb visible light. So they are, of course, then colorful. So they are, in this case, I think this is a red polymer. And the problem is, compared to silicon, in silicon you have single crystal. You have a crystal structure which in a solar cell is more or less infinite. Yeah? So in organic materials you have single molecules. So you're working with molecular semiconductors, and therefore you don't talk about conduction band and valence band, yeah, which you have in silicon. You talk usually about molecule orbitals. Yeah, so from the frontier molecule orbitals, you have here the highest occupied molecule orbital, which is occupied by electrons. Yeah, this is more or less the valence band of an inorganic semiconductor. And you have then unfilled, unoccupied molecule orbitals. These are called LUMO, yeah, which are the empty orbitals. And the first process which has to take place in a solar cell, in every solar cell, is the absorption of light. And what happens if a photon is absorbed? It, of course, give an electron the energy to come from the HOMO to the LUMO, so from an occupied orbital to an unoccupied orbital, or in an inorganic semiconductor from the valence band to the conduction band. Now, because you have a molecule, it's a molecular semiconductor, yeah. This electron, of course, has created a hole at the same time, and they, of course, are bound to each other by Coulombic forces, and they are still on one molecule. So the recombination, so the electron very easily fall back to the ground state, yeah, to the HOMO, sometimes by fluorescence, sometimes just by terminal deactivation, and you don't get a lot of electricity out of it, even if you have two electrodes, you have this material in between electrodes. So the trick in organic photovoltaics is that you don't have only one semiconductor, that you have two semiconductors which you combine. And the first working solar cell was even this MDMO PPV with this Buckminster fullerene. You can argue if it's an organic or an inorganic material, yeah. But nevertheless, it's also a conjugated system, yeah, which actually has HOMO-LUMO levels which are shifted. So the energy is lower in the carbon-60 than in this so-called paraphenylene-vinylene, or shortly PPV derivative. So what happens now is that actually the electron which is now in the LUMO does not fall back, it is transferred to the carbon-60, because you have here an energy difference, so the electron can be moved to the carbon-60. For chemists, this sounds, so the physicists always say an electron transfer, yeah. For chemists, it's a redox reaction. Yeah? So actually, the carbon-60 get reduced and the PPV get oxidized. Yeah, so it's a photo-induced oxidation reaction. Okay, and now you have an oxidized and then reduced material, and then actually from one carbon-60 to the next carbon-60, the electron travels to the electrode. So you have actually a reduction reaction from each carbon-60. So it's a more or less a hopping mechanism, if you want. Okay, there's some problems with this graph actually. Yeah, I'm sorry for this because the first slide we checked, but not in the middle. Yeah, sorry. There is some. I think I can do it without colors. Yeah, because you see always you have two materials actually. The organic semiconductor on this slide. Oh, I will. Yeah, on this. So you have a different step of the organic solar cell. So actually, you have the exciton formation. This is what is this done. This is the formation of an electron-hole pair. Yeah, which is of course has a nano domain in the material. Yeah, so it has to come to the interface to the other material. So this electron-hole pair has to travel, and this is actually shown exciton diffusion. So actually, this electron-hole pair travels to the interface, then it splits up. So this is this electron transfer or redox chemistry, and then you have the charge transport to the electrode where you have the charge collection. Yeah, so I think I skipped this slide because, yeah, coming to the next one. So if you want to measure a solar cell, actually, just the most important parameter, and I just shortly come through what was said. So actually what you're doing in a solar cell is that you shine light actually on your solar cell and you measure your current voltage diagram. So you change the voltage and you measure the current which you get out of the solar cell. And actually you see in this region here, you produce power. Yeah? But as just for all of you, just as a reminder, so power, electrical power is the product of voltage multiplied by the current. Yeah? So for each of this point, you can have a certain power. And at one point, this is the so-called maximum power point, you have the maximum power of your solar cell. This is then shown here. So usually you have two different other values here. This is the so-called open circuit voltage and the short circuit current density, short circuit current, where actually we have the maximum current, but you have no voltage, so you don't produce any power. And here the same, you have the maximum voltage, but no current, you also do not produce any power. But usually these are quite significant points for solar cell, and if you have the important table of a solar cell, you always find this key figures. So actually how you define the power conversion efficiency of a solar cell. In principle, you look what light, the power of the light which is shine on your solar cell. So usually you work with artificial light with 1000 watt per square meter, and you look out how much power you get. Yeah. So this is the electrical power which you get divided by the light power. And usually this can be explained by the voltage, the current, so the VOC, the ESC, multiplied by the fill factor, and the fill factor is this area. So what is the maximum power divided by the ideal maximum power of an ideal solar cell when you don't have actually like a rectangular here. Yeah? So with this ESC and VOC value, the maximum ideal solar cell, which you never can get, yeah, would be this rectangular, and the fill factor just gives you an idea how good the solar cell is. So you can reach 80%. This means it's a very good solar cell. So 85%, even 90% is possible, but not more. So you find usually these values, the power conversion efficiency, VOC, ESC, and fill factor. And also in my presentation, you will find these key figures sometimes. Okay. Yeah, this actually brings me. I have already said that you need two semiconductors, and of course there are two different possibilities how you can arrange these two semiconductors. So of course you can do it like in the silicon world, PN junction, yeah, like a B layer, where you have one phase is so-called donor phase, which is the phase which is oxidized, yeah. Also the B-type semiconductor, and the acceptor phase just one layer on top of each other. Or what is much more often seen in organic photovoltaics is that you have a so-called bulk heterojunction, which is just a mixture of both. So you make a mixture of both to create a larger interface, because the most crucial step is this electron transfer to the other material. And by this, of course, you increase the interface between this material, and this exciton dissociation, so this redox reaction is much more easily happening. However, the transport is a little bit more complicated. Here you don't have any problems with the transport. Yeah? Here, of course, you have much longer ways, and there might be also some isolation materials. So this is the trick in organic solar cells, actually, not only to have good material, but also to optimize this so-called morphology of the solar cell. I will show you some examples from the literature, yeah, how important this is actually. This is one of the first one, this MPMO derivatives with fullerene. You see, depending on the processing, so this was processed from toluene, and this was from chlorobenzene, very similar solvents, but differently, yeah. And I think you see by just visible that you have here very large agglomerates, and here you have a very nice smaller agglomerates with higher surfaces. So, and you can, of course, also think which was more efficient. This one was much more efficient. Yeah. With some numbers, I show it on the next slide. This is one of the working cores for a very long time. This was a called P3HD polymer with also a fullerene derivative. And actually, this was, if you spin coat this, so if you make a coating of these materials together, you see just a grayish surface, because they are really, really intermixed to each other. Yeah? So you see perhaps here a little bit these fibrils, which are coming from the polymer. So this is a sketch, how the scientists thought that it looks like. So you have these polymer fibrils, and then you have a homogeneous mixture of the material. And the solar cells is this blue curve. It's a very bad solar cells, around 2% actually. Yeah? And actually what they did, then they make a thermal annealing step of 150 degrees. So the polymers start to agglomerate, they start to crystallize. And after this step, only for 10 minutes, you see black. I think you can see this different morphology. Yeah? So you see black spots, you see also larger fibrils. Yeah? So you need the morphology, the interface for sure is lower, yeah, than in the first one, but you have larger object also. And then actually you see that the red curve, I think you clearly see it, that it's much more efficient. So you double more, the efficiency was doubled more than the original case. The reason is that, of course, you need this interface. It's like your blood vessels. You need the small blood vessels for the interactions with the cells, but to move the blood to the heart, you need the large vessels. Yeah, you need the artery, so the aorta and so on. Yeah? And it's the same with the solar cells. You need areas which are having high surfaces, but you need also these agglomerates, which are the highways for the electrons and holes, so that this can be then traveled to the electrodes. So this is the trick of organic solar cells a little bit. And this is our next one. I see some representation. Yeah? So you need some regions where you have really pure phases, where you have no problem that the electron, for example, can travel here and the hole can travel on the red phase. So this is one of the things which happens. You have already seen there were not only the PPV and the fullerene material, we have already seen also P3HD. And I don't just want on the next slide, OPV is not one material, they are different materials. So the basics of the theory was mainly done by the fullerene base, so this is the fullerene base, but you see since a few years a lot of different other materials have overtaken the fullerene as acceptor materials, and they are allowing now 18% plus efficiency. And this is organic chemistry, so I don't know how many people know organic chemistry. You find a lot of different materials, and that's also the beauty of organic solar cells, but of course also the curse, because you have so many materials which you have to optimize, yeah, and you need always a combination of at least 2 of these materials. So you have a lot of materials and a lot of combinations. And just on the next slide, this is just from a review we have done, a very, very tiny selection of some materials, yeah, which have been published, I think, in the last 4 years. Yeah, and there is, I think, 10 times more, or even 100 times more of materials which are published since the last 5 years. And I think every week there are 10 new materials. Yeah, yeah. This is actually state of the art for PM6, Y6. I don't give the chemical name, it's a very long name for 2 lines. Yeah? So usually you work with the abbreviation. So this is actually the material which is called donor, which is oxidized, and this is actually the acceptor material. And this is actually materials which you can buy today. Yeah? And this is done usually with commercial available materials, which gives you 70%. With a little bit training, you can really make your solar cells in your own lab, which is not possible, I think, with silicon solar cells. Yeah. And this is just the external quantum efficiency. This means the electricity by the wavelength, and you see it really covers the whole visible range, even in the low infrared region today. Yeah, so you can really cover the whole visible spectrum. I have just to look how much. Waste time. Okay. Yeah. So this was state of the art. What is organic solar cell? I just now in the next slide I will show you 2 examples how we doing research. So we of course thinking how we can improve, and of course sometimes it doesn't work out as we thought. Yeah. I just want to show what we are doing. So I'm a material chemist. Of course I am interested in new materials. So we have one idea how we can improve organic solar cells, and this was actually based on a theoretical paper, yeah, that if you can increase the permittivity of organic solar cells, so organic solar cells are having a very low permittivity, around 2, usually 2.5, and there was a prediction that if you can increase the permittivity of a solar cell, you can greatly enhance the efficiency. So how you can increase the permittivity? Actually by increasing the polarizability of your material. And this you can actually do by introducing polarizable side chain. This sounds a little bit perhaps strange, yeah? So what do we mean with polarizable side chains? This might be here, for example, side chains which are with having ethylene glycol, or for example here, sulfone side chains. So these are materials which are, so the main materials are mainly carbon and hydrogen and sulfur. Here oxygen always is very polar, it introduces polarity. So actually we compare these materials we have synthesized already some years ago. So we want to compare these materials with ethylene glycol or these sulfone containing materials. I will focus mainly on this material, yeah. Not to bore you too much, yeah. Of course, first of all, you have to synthesize it, yeah. So what we are doing is actually we're going into lab, and we have at least 1, 2, 3 steps actually of synthesizing that we have this material, and in between we have always a lot of cleaning, of purification step. We have to make the characterization, so we have really to prove that this is the structure we have, yeah. And then we have hopefully enough material to make further research. Then of course we have to determine the optical properties. So we have to measure the optical spectrum, we have to measure usually the fluorescence in solution, in thin film. We measure the thermal stability, for example, or we measure also by cyclic voltammetry the oxidation and reduction of the material actually, yeah? The homolumo level. So we do a lot of characterization, but we have not built any solar cell with this material. Yeah? So this is already before we need, I would say for this material, although the synthesis is quite easy, we need at least 3-4 months before we can even start to build solar cell. Then of course in our case we have of course to prove that the permittivity is really larger, because this was our idea. And this is actually a comparison of these 2 materials with the pure alkyl side chain. So this is the original values, and you see in both cases we get a strong increase of the permittivity of more than 50%. I think this is shown here, yeah. So we have here an increase of the permittivity. So actually the material is as expected. However, then the trouble starts with making the solar cell, because now you have to find, we're making it from solutions, you find a good solvent. So you have to look which solvent is working, and you see that we have no real good solvent where this, our new material, this is the material, with the other material is really good soluble. Yeah? So this actually brought, in this case, brought some, so you see here it's a good solubility, but here it doesn't. With chloroform you have always troubles, yeah, so we don't use it too often. So actually we started in this case because this is the usually strategy to use this bulk heterojunction, yeah. But in this case, if you have two different solvents, it's usually much better to use this B-layer approach. So we go back and say, okay, this bulk heterojunction approach is nice, but in our definite case, it's better to have this B-layer approach, and it's probably too ideal because probably the surface is rough here, yeah. So you have an intermixing nevertheless in the surface layer. Okay. Then, of course, you have to optimize your solar cell. So you have to build up your solar cell on a glass substrate, which is covered by a transport electrode. Then you have a selective contact. And then you have your active layer. And then you have your interface layer. And then you have back electrode. So it's not only the material, you have to optimize every single step. So this optimization of the solar cell, it takes also a long time. Yeah, so it's not, so this also you have to invest a long time here. And actually in this particular case, sorry. Oh, okay, yeah. Sorry, these are the solar cells. So we are making small solar cells. These are for research, so not to waste too much material. Yeah, we have very small solar cells. So this is 1.5 centimeter. Yeah. So here we test the material, and if we see it's working, then we are going to larger areas. But this material, the synthesis, usually gives you 100 milligrams, yeah, and yeah, so you don't want to waste your material. Yeah, so actually you have a lot of different factors which can influence your performance. So you have, of course, every layer, the layer thickness, the solvent, there is some post-treatment, the ratio between these two materials. So you have a lot of different parameters, and actually in this case, we tried to do it by a design of experiment studies. So we do some statistical, setting some statistical parameters and really trying to find the optimum, varying this, finding the optimum parameters. Actually, it worked quite fine. Yeah. So by changing different temperatures, actually, so you see, we did it by 25 degrees or room temperature, slightly above and 150, and we changed the film thickness. Yeah, we really found a sweet spot where we say so we didn't do this experiment. This was just a prediction. If we would process under these conditions, we should find the optimum conditions. And actually, it turned out it was really the sweet spot, and we get the best efficiency under this one. So, but if not, if you don't do this with a statistical approach, yeah, you have to do a lot of experiments. So you have probably thousands of different combinations. Yeah, and actually it turned out that we get a slightly improvement. I just perhaps a little faster. Yeah, so our solar cells were slightly better than the solar cells without the polarizable change, but it was roughly 5%. So we are far away from the 19%. Yeah, but nevertheless, it was one of the rare cases where we really can show that this improvement in permittivity increases also the power conversion efficiency. So we were quite happy, and we could publish it in a paper, but for real applications, it will never work. Yeah. So this is also science. So this is what we are doing, and sometimes not everyone gets high efficient solar cells. So this is just a summary of this. Yeah. So we get really slightly better solar cells with our approach, but it was not world record breaking. So actually we said, okay, why we should not try it also with this high efficiency? So this Y6 was the state-of-the-art material, which gives up to 18%. Yeah? Why you don't do the same strategy now with this high efficient materials? Okay, we also tried, but of course it's a little bit more complicated. You see already the synthesis, it's much longer, and it took us 1 year to have the material. Yeah, so it's not that you say we have an idea and tomorrow we have the material. It took us 1 month actually to synthesize the material, because it's a multi-step synthesis, and also some of the idea how we do it the best way sometimes turned out it was not the best way, yeah, and we have to restart it from the beginning. So it's quite tedious for a chemist. Nevertheless, we get the material. We also show that the permittivity was really improved. So compared to the basic material device 6, the commercial one, yeah. So we get a very large increase in the permittivity, and we're very hopefully, because in the other one we saw that we get an increase in the efficiency. So we also built solar cell, but this was the record efficiency with this new material. So we didn't get 60, 70%, we get only 8% or 5%. So what we also usually do, we don't only build solar cells and optimize the solar cell, we're of course thinking what might happen. So we also investigate, of course, the morphology, and how you can investigate the morphology by making different other materials. So we really tried by IFM, GVAX measurement, TEM measurement to investigate what's happened. So if you just look on the IFM, what is IFM? So I'm not sure if everyone is familiar. So actually it's you image the topology. It's like a relief structure of your surface, yeah, by having a tip actually, which is actually, it's not scratching your surface. So it's this tip actually scans your surface, yeah, and you have a deviation which can be measured very accurately with a laser, yeah. So actually this tip, so the exact position of your tip actually is monitored by a laser, and this is the morphology. So and then you have here the surface image of your material. There are different modes, yeah. Usually you don't have it direct contact, but you can have also direct contact, so usually you can have also an amplitude mode, yeah. And actually you see here the surface morphology of all of different materials. So this commercial one, but also our synthesized material, they look a little bit different, but if you look on the scaling, it's very similar. Yeah, it's not explaining everything, especially here. This is the so-called phase image, because you see a little bit of the chemical structure, I would say, yeah, or physical structure. They are very, very similar. You don't see very large issues. So this could not explain why you have these large differences. We also even investigate more. So we have also studied by grazing incident wide angle X-ray scattering. So what you're doing here, by an X-ray beam, you, with a very special angle, you shine X-rays on your substrate, and you measure the scattered light. So like in a classical crystallographic experiment, yeah. And actually, depending what type of structure you have, you get different signals. Yes, you have a 2D detector, and these actually are the different materials. So you see some differences. Yeah, you see that you have here perhaps a little bit higher orientation or higher crystallinity in our material, but not that large, especially if you're looking also in the electron microscopy images, which is shown on the next one. Yeah, you see actually, the green and the red is the two different phases. You see similar structures. And from the experience, this cannot explain these very large differences. So we're really a little bit, so we didn't know actually what happens really, because the electronic structure of the material is totally the same. This I forgot to say, yeah. So this, where is the structure? I just go back, yeah. So actually, these glycol chains here are not connected to the electronic structure of the material. So you have the same optical spectra. So they have the same UV vis absorption, you have the same CV, so it's the same electronic properties, yeah. So it's really only the side chain. They are not connected to the electronic system, yeah. So this is very strange, yeah, and we thought it's very strange. And actually at the same time, we already speculated that it might be to do something with the electronic disorder, which is also, people were thinking about it. And at the same time, actually, I think 1 month before or after us, yeah, a Chinese group, together with a German group, actually published a paper having very similar material synthesized. So they have also these ethylene glycol side chains with different ones, yeah, but the same idea, and they also found out they didn't get better solar cells with it, and they just make a little bit more into electronic investigation, they found out that they have a higher electronic disorder, which just actually destroy the good electronic properties. So this is also research. Yes, you have a good idea, which in principle should work, but then the details, then it's not as well. Just coming back to the state of the solar cells, because also in my title I promised you to tell you about the weaknesses, about the stability. Yeah? These materials are really good, giving good efficiency. 70% would be really, really nice and would be sufficient to make it a really flexible product which are on the market. You would have some applications and you would have the market and this could be sold. But the stability is not there at the moment, because the problem is, if you look on these materials, yeah, you see if you just have here the time and the efficiency here, yeah, you see that you get a very fast degradation. So this is 1,000 hours, yeah. Then you have only in most cases, or in some cases even below 60% or 65% of the original efficiency. Yeah. The main thing is that the fill factor, and this is shown here, yeah, so you see that the fill factor gets more or less destroyed, but you lose every parameter. Yeah. And this doesn't matter if you have here the Y6 or other derivatives. Yeah, some are a little bit better. So you see this a little bit better perhaps than this one. Yeah, so this is actually at the moment the most important thing, how you can build better structures. Yeah, there's also an idea what happens. Yeah, so actually what people believe is that this. So if you just go back, this is actually this group here. Yeah, so I don't want to go into the chemistry. Yeah, but actually this group actually can under light photoisomerize, and in this configuration with oxygen actually they form actually a oxyrane ring and destroys the conjugation and destroys then the electronic system, because this double bond is of course here connected and you destroy the conjugated system. And you see of course one problem is that you really have to exclude oxygen, but nevertheless also this rotation, there are some other side reactions which can take place. So the problem is really to go, and this is good for me as chemist, to find structures which where you can block this rotation and where you can block this photoreaction. Yeah. However, there are some other issues which I also show you from our own research. Actually, you see these fluorine groups here, and in organic solar cells. This is, sorry, I will just, so we have here also, so we have a lot of fluorinated compounds at the moment. So the state of the materials always contain fluorine atoms, And this I forgot to say perhaps, you see, this is actually a tandem solar cell, but you see here the thickness of an organic solar cell. This is actually here 200 nanometers. So this is actually the active layer, which is not even 200 nanometer. This I forgot to say, this 70% of power conversion efficiency is just given by an active layer of 100 to 200 nanometer. Yeah, this is incredible thin. A silicon solar cell has 100 micrometer to 200 micrometer, so you have a factor of 1,000 lower from the film thickness than a silicon solar cell. Even you can imagine that the synthesis is quite expensive, but the film is so thin that you can really, let's say, with 1 gram you can already cover quite a large surface. And 1 kilogram, I think you can even, I think 50,000 square meters you can cover with 1 kilogram of organic solars, of such an organic semiconductor. So it's incredible thin. But nevertheless, what we found out by this, so actually we wanted to do something totally different. So we really want to make tandem solar cell, and just wanted to analyze it if we have a nice cross section, and we used here a molybdenum oxide aluminium layer, and aluminium is also sometimes used as back contact, as electrode, because it's very cheap. It can be evaporated easily. It can also be printed in some. Print is not so easy, but it can be easily evaporated. So it would be a cheap material as back electrode. But what we found out actually is that in this layer where we have aluminium, we found also a lot of fluorine. So that it means that the organic fluorinated compounds are not stable in the combination with aluminium. So there are also some other issues which with the stability of organic solar cells, which are at the moment not totally known. Yeah? So there are also some other issues which have to be resolved. With silver, it's much better. Yeah? So silver works better, but of course it's also more expensive. Yeah, this is just we also with TOF SIMS with a different method. We just also proved that we find the fluorine because you have also to check that you don't have any sample artifacts. So with two independent methods, we really proved that the fluorine and the aluminium is reacting with each other. Yeah, actually with this already, I think I will perhaps also conclude. Yeah, I hope that I have shown to you that organic solar cells, it's not like silicon, one material, and also in silicon there's a lot of different technologies. Yeah. In organic solar cells you have a lot of different materials, a lot of different combinations, and I think we can, and therefore it makes it difficult, and probably we will have to do a lot still just looking at the different materials we have already. Yeah. Then of course the organic semiconductors are expensive because of the complicated synthesis, but the active layer is only 100 nanometer or even perhaps 200 nanometer in some cases. Yeah. So actually the pros, organic solar cells can already today reaching 90% efficiency. They can be easily processed by roll-to-roll fabrication methods. Yeah. This I have not shown you, but we have also done this ourselves in our lab. Yeah. They can be really flexible. They can be semi-transparent. Yeah. But the drawback is the current materials are not as photostable as needed. Yeah. And this is really the drawback of current materials. And of course, during my research, I think we have a lot of people have contributed. I said, it's not the complete list because I worked 20 years now. Yeah, so it's really the people who are working on the organic solar cell in the recent 5 years, I would say. We have a lot of collaboration here. Also, of course, a lot of funding. And yeah, with this, I want to thank you. And yeah. Okay.
Okay, Gregor, thank you for this nice presentation. I think we have some questions. I will start to warm up. The first question is, when do you expect that we see organic solar cells on the market?
This is a good question because you have still some companies which are really trying to bring it on the market, and you see already some demonstration objects, and every year there are new ones which are installed. So you have installations from Heliatech or from now it's called Askar Solar Power Films. It's now owned by Herringbau, which are also still producing solar cells on a roll-to-roll fabrication. But they are not really, you can not say, okay, I want to buy it. You have to make a project with them together and they make some demonstrations. Yeah. But there are already companies really trying to bring on the market. But of course, since 10 years, I have to say. Yeah. Yeah, but if somebody can really have solved this issue, at least making the solar cells stable for 5,000 hours, I think they will be really on the market for, let's say, not for the rooftops, but for tents or for some, let's say, small gadgets and so on, yeah, where you don't need this very long stability.
Okay. If anyone has a question, just raise hand. Yeah, Matthias.
So I'll start with something easier. You're from Austria. I'm sure you're aware that the fluorine was just banned from the ski waxes. The fluorine was just banned from the ski waxes, just to conserve the nature. Now introducing fluorine through other technology is a little bit questionable. How do you comment on that?
This is a good question. I think usually I have to look at the list because it's a little bit complicated. We don't have perfluorinated compounds because it's not like Teflon where you have carbon fluorine. So we don't have any CF3 group or any CF2 groups in there. So we have no alkyl chains actually. We have aromatic ring systems. They are not so stable like the perfluorinated. Therefore, they are not so problematic. Yeah, but I don't know. Actually, we have to look at the regulations, but at the moment, the most crucial things are things like Teflon or something like this. So it's not comparable with these materials.
Thank you. And another question. I've seen you have done grazing incidents on your films. Now you are working with the complex molecules, and I'm aware the excitation happens within the molecule. But have you seen a significant periodic ordering in your films of these molecules, and how that would then influence the electron transfer mechanism?
Yes, you have already seen that we have some peaks there. So we see some ordering. It really depends on the material. Some of the material are even crystalline or semi-crystalline. Yeah? So you see, and there are also some materials like the perilanes, which are sometimes really crystalline. The problem is we don't want to have a too high crystallinity, because the crystals, we have only a layer of 100 nanometer, 200 nanometer, and crystalline materials, if it's crystallized from solution, they form small crystallites, and usually you then have pinholes in between the crystallites. So we need some continuous layer, and if you have it too crystalline, you have the problem that you have pinholes, but of course the charge mobility would be much better in a crystalline material. So a little bit crystallinity we like, but if it's too crystalline, we usually get problems with pinholes and shortcuts, the other short circuits done. No?
Thank you.
Any other questions? Yes.
So what about the production process? I mean, we know that solar cells are really nice for converting energy. However, the production process can be rather heavy for the environment due to acids and stuff like this. Is there a different process?
Actually, this is of course always true. So we have also a carbon footprint for our production. This is clear for everything. There are some claims that OPV, if you have always this energy payback time, that OPV can reach payback times of 2 months or something like this. So they are very, very short, because you have a roll-to-roll, a continuous machine. I have not done these calculations, so they are believed that they are really more efficient than silicon, because you don't have any high temperature processes. And however, you have your complicated synthesis. So this really depends on which materials you use. There are, of course, this Y6, this is a 15-step synthesis route, which is also therefore not really good. But there are some other materials which only need 3 to 5 steps, which are then better. So it really depends also on the material. But then, because as I mentioned, 1 kilogram can coat 50,000 square meters roughly. I hope, or 5,000 or 50,000. It's a huge number, nevertheless. So even though it's perhaps you don't need a lot of material. So I think this is not the problem. It's more which type of substrates you're using, which type of machinery you use. Of course, the solvent is a problem. Sometimes you need, but you have also. We use very often chlorinated solvents, but you can also use non-chlorinated solvents. It's not water, it's clear, so this might be an issue, but it's not like we don't use anything like hydrogen fluoride or something like silicon. Those we don't use usually.
Okay, regarding that, I have a question, because Europe accepted this Green Deal,
yes,
which somehow forces us to use less fossil fuels, less plastics. So how do you think this will impact organic solar cells? Because they're made out of plastic, no?
Yeah, but plastic is not plastic, I would say, because also in a silicon module you have plastic inside, no? Because you have your silicon solar cells are embedded actually. You have the glass slide, and then you have a plastic foil, and then you have the silicon solar cells. And then you have another plastic foil, and then you have either a plastic back sheet or a glass slide. You have also here in the classical silicon solar cells, you have a lot of plastic integrated. Here, if it's really, if it's, I think, if it makes sense, I think it will not bend, yeah, because of course you have to look at the recycling possibility. This is clear, yeah. This depends mainly on the substrate, I would say, yeah. But I don't see any problems in regard to this, yeah, because you also would not ban plastic from the car. You have a lot of plastics in there, but if you go back to metals, the weight will be heavier, and then you will use more energy to. So in some, I think plastic will not ban in every case, no?
Any questions more? No. Then just one question which you don't need to answer. So it is time to start to invest in this, to open the business of producing solar cells or not?
This is a good question.
No, we can discuss later.
I don't know. So if you have a lot of money, and I think it's not that you can produce it in 5 years. Or probably you can produce it in 5 years, but it depends.
Because maybe I'm following this Heliatech company,
yeah,
which started claiming that they will sell solar cells already, I think, in 2006, no? But still now, I was trying to buy one solar cell. They didn't reply to my mail.
Yeah, there is some strange things. So, for example,
they just asked me if I need 10,000 meters or not.
Yeah, I think there was a company, this Danish company, Infinity PV. I think they sell some organic solar cells. So Thomas bought some of them. But actually now, I think you cannot buy it anymore. They just sell equipment for making solar cells, but not the solar cells anymore. But perhaps I think they have a collaboration with another company, which I think producing now solar cells. So perhaps this is the reason. I think the main issue is really the stability. So if you, and here a lot will be done. So we have also now a large project on stability of OPV, yeah? And people are now understanding more and more what is the reason behind this, yeah. But of course, I would not invest in a company who really wants to replace silicon solar modules on the roof. This, I think, no way that this will be happen in the 10 years. But if you have a business idea to make solar cells for, I think, outdoor applications, and you have a really good model, and I think if you have a good idea how you can package it, yeah. So if you have a good idea how you can block the oxygen here, then I think it's worth perhaps.
Okay, let's thank the speaker again.